Hi guys, good morning. Are you able to hear me? Guys?
Yes, sir.
Yeah. We'll wait for 5 minutes. Let your friends join, then we'll start. Guys, in this, how many of you are already going for JE coaching or something? Rohan, Shruti, Surya, Venisha. Is anyone going for JE or NEET coaching?
I'm not going.
No, sir, I'm not going. No.
No, sir.
Okay. Okay. So are you guys planning to do it? Are you guys planning to write JE or NEET after your 12th?
No, sir.
I'm not sure yet, sir.
Okay. Because if you want to start, 11th is the right time to start. It's actually already late. So you have to start just when your 11th academic session starts. And hope you know there is going to be a course which is going to come in Epsilon itself for JE and NEET. Did you get to know about the information?
Yes, sir.
Yeah. Another minute will start. Okay. Fine, we'll start. So, guys, tell me what was the last thing we saw? I just cleared the board also. Hope you remember what we saw last part of the class. So I think I introduced you to a concept of something called as coordinate bond,
Yes, sir.
right? So what do you remember about it? What is special about coordinate bond?
The shared pair of electron would be from the same atom.
Exactly, right? So we know that for a covalent bond to be formed, right? For a covalent bond to be formed, I require two electrons, right? So in a normal covalent bond, electrons are going to come from two atoms. One electron each are going to come from one element, right? But in case of a coordinate bond, both the electrons are going to come from a single atom. And we saw the example for carbon monoxide, where you saw oxygen is giving its lone pair to carbon, sharing it. So thereby, I have a coordinate bond there. Cool. Okay, so we'll take one more example. Like I think Rohan, you asked for N3 minus, right? So we'll
Yes,
see
sir.
how we are going to have a bonding structure there. Okay, fine. So N3 1 minus is what is the charge? I mean, is what is the formula, right? Say I have three nitrogen atoms. Okay, now you can see that N3 1 minus, right? So definitely whenever you have negative charges, it is going to go to the bonding atom. So okay, or now for now understand that either of these three nitrogen atom are going to have one negative charge, right? And whenever you see a negative charge, you should not put it on the central atom. That is, this is the central atom here. Here you should not put. Either you can put it here or here. Not only in this case, any of the cases for the matter, if you see a negative charge, it has to go to the side atoms, not the central atom. Okay, that is the first rule. Again, we'll see why is it like this and all that when I go further and further. But for now, please understand that either this or this nitrogen atom is going to have a negative charge. Cool. So say I put this nitrogen atom to have a negative charge. Okay. Right. Cool. So I know nitrogen atom is going to have 5 valence electrons. 2,5 is the configuration, right? Say I have 5 electrons. 1, 2, 3, 4, 5. And this okay, I'll put it like this. Okay. And this nitrogen atom is having N minus. So instead of having 5 valence electrons, it's going to have 6 valence electrons, right? So 1, 2, 3, 4, 5, say 6. No problem. 1, 2, 3, 4, 5, 6. Cool. Right. Again, same way, this nitrogen atom is going to have 5 electrons. No problem. Okay. So one of them is having a minus, another two are neutral. Okay. So let me go for the bonding atoms first. So I think I have to put this electron here. So this nitrogen atom, I mean, this N minus has 6 valence electrons. It requires 2 more electrons to satisfy its octet. So, done. Right? Okay. Now, this nitrogen atom requires 3 electrons to satisfy its octet. Right? This nitrogen atom requires 3 electrons to satisfy this octet. 1 second, guys. 1 second. So 2 electrons. If this gives 3 electrons and this, I cannot have 5 bonds. What happened here? Say one of them was coordinate bond. Okay, we'll not do this first. Okay. Okay, this is actually going to be a complex thing, is because you are going to see that nitrogen atom is not going to satisfy its octet. That's what is going to happen. Okay, I'll tell you how. Say now one is done. So okay, say one more. And this, if I put it like this, I'm going to have, don't care, 1, 2, 3, 4. No, single electron is there. Okay, here 2 bonds are gone. 3 electrons. Here there are 6. 2 are bonding. 2 rotates. There is 1 electron here. What happened? What am I doing wrong? Or if this say n, so 2 plus 1 becomes 3. Now, I think I got it. One second. Okay. So yeah. So this nitrogen atom requires 2 electrons. So it's done, right? And say I form a single bond first, right? So I put it like this. I use some other color, and I put 2 more electrons here, right? So now this say I'm going to have first bond getting formed here. You see that there is one bond getting formed here, right? Now if you look at this nitrogen atom, it has 5 valence electrons. Now one more electron is coming from this nitrogen, so it is 6 valence electrons, correct? Now for this nitrogen atom, I have to satisfy octet. So what is going to happen? Now these 2 electrons are going to get shared as a coordinate bond to this nitrogen, correct? So now how will I draw this? Now if you look at this, okay, now for this nitrogen, there are 5 valence electrons, 1 electron coming from here, 6, and 2 more electrons coming from here, totally 8. So I am going to have 1, 2, 3, 4, 5, 6, 7, 8. Yes, all nitrogen atoms after dissatisfied, and there is one coordinate bond. Now how will it determine, write the bond structure? So I have a double bond here, right? I have a double bond here. So N double bond N minus. And for this, there is a normal single bond with this nitrogen, and there is a coordinate bond. There is a coordinate bond between these 2 nitrogens.
Sir,
Okay.
Sir,
Yeah.
sir, on the first diagram you drew 3, you know, sir. First gen was having
First one,
electrons.
6
Second one
electrons. The first one here.
was the left hand side, sir.
Okay, here are 5 electrons. Okay.
Then the second one also had 5 electrons.
Okay.
Then the last one had 6 electrons, no, sir, including the
Last one. Yeah, including the negative, 6 electrons.
the last electron, you could split it as 3, 3, no, sir. Like 3 electrons one side and 3 electrons on other side, so that it will get satisfied, no, sir.
But the thing is, nitrogen cannot, like any nitrogen cannot have 5 bonds. It's not possible. So the thing is, there are something called as expanded octet, right? So we'll see, we'll speak about it in a little while. But for now, please understand that nitrogen maximum only 4 bonds are possible with one single nitrogen. More than that is not possible at all. Is that okay?
Okay, sir.
Right? You will get to know about this reason in a very soon. As I continue, you will get to know why is it that nitrogen cannot have 5 bonds. But if I go for the same period, so if I go for the same group, that is, if I take phosphorus, right? Phosphorus can have 5 bonds.
Sir?
Yeah.
Sir, the left hand side nitrogen, why there is only 4 electrons, sir, instead of 5?
5 electrons are there. Oh, sorry.
You missed one.
Yeah, 1. Right? Fine. So there are 5 electrons, 1 electron coming from here, making it 6, plus 2 electron, making it 8. Right? And for this, already 6 electrons, 2 more electrons coming here, making it 8. And for this nitrogen, already 5 electrons, 5 electrons and 1, 6, 6 plus 2 is 8. So everything is done. Everybody understood how the structure came, guys?
Yes,
Please
sir.
give me a yes.
Yes, sir.
Okay, cool. Now we are going to take one more example, right? Now we are going to take H2SO4, right? Now you can see, you can tell me that, sir, we already saw the structure for H2SO4, isn't it? We drew the Lewis dot structure that day, right? But there is for a single molecule, right? For a single molecule, there can be more than one Lewis dot structure, right? And both are correct, actually. Theoretically speaking, both are correct. It's all about how you interpret that particular case, right? So for the same H2SO4, if you can remember how I drew the structure, it would have been something like this. Right? Say it would have been sulfur, H2SO4, I'm sorry. This would have been the structure for H2SO4, right? 2 hydrogens and 2 oxygen atoms. Done. And 4 oxygen atom and 1 sulfur. Right. This is how you would have drawn it. And you can easily go for the Lewis dot also. Right. Okay. Now, do you want to do that again? Fine. We will do it. Right. So let me take out the hydrogens. and put it as O minus and O minus. Okay, fine. So now we'll draw the normal Lewis dot, which we already saw. So sulfur is having 6 valence electrons, 1, 2, 3, 4, 5, 6, right? And 2 of the oxygen atoms are having O minus, right? So instead of having 6 valence electrons, they will have 7, right? Okay, so O minus, so we'll have 7, 1, 2, 3, 4, 5, 6, 7. Same way, okay. Another oxygen atom is having O minus, again 1 electron. Oh, it should have 7. Okay, so there is one more with a negative charge. Okay, fine. So this is done. Now, there are two oxygen atoms which are neutral. They are going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. Same way here. 1, 2, 3, 4, 5, 6. Okay, now it's very simple. Now this oxygen atom requires one more electron to satisfy its octet. So it will take up this electron. Again, same goes with this. This oxygen atom requires one more electron to satisfy its octet. Again, done. And this oxygen atom requires 2 electrons to satisfy its octet. That is also done. And this oxygen atom also requires 2 more electrons to satisfy its octet. Done. Now whatever the sulfur atom gave, that many electrons it will take also, isn't it? So 1. Yes. So this would have been the structure. And if you look at this is what you would have got. No problem, right? But the same thing can be explained with the help of a coordinate bond, right? Same structure, which I have here, right? Can be explained with the help of a coordinate bond. We'll see how, right? Okay, so we'll try to do this. Right. Again, sulfur having 6 valence electrons, 1, 2, 3, 4, 5, 6. Oxygen atom having minus charge, so 7. So 1, 2, 3, 4, 5, 6, 7. Same way, this oxygen atom minus or 1, 2, 3, 4, 5, 6, 7 with a negative charge, and 2 oxygen atoms are going to have 6 valence electrons. Okay, done. So for these 2 oxygen atoms, it is going to be same, right? For these 2 oxygen atoms, say it will take 1 electron, it will take another electron. Done. These 2 O minuses are done, right? Say I'll take one. This oxygen atom also requires 2 electrons, so I'll just take this also. Okay. Now, for this oxygen atom, instead of sharing these 2 electrons and getting 2 electrons back, right? This electrons will go here, this electrons will come here. I'll make a double bond, just like how I did here, right? Instead of that, I can make a coordinate bond also. How will I make? I put this electron here, and these 2 electrons are going to go to oxygen. Octet satisfied, right? It requires 2 electrons. However it goes, it doesn't matter. Either I'm going to form a 2 double bond, right? Or these 2 electrons are going to go to oxygen atom in the form of a coordinate bond. Either way, this oxygen atom's octet is satisfied, isn't it? So now how will I represent the structure? The structure would have been 1 O minus, another O minus. I had a double bond over here. See, I had a single bond, single bond, single bond, single bond. There's a double bond. At last, for this sulfur and this oxygen atom alone, I am going to have a coordinate bond. That's it. Guys, did you understand what happened here?
Yes, sir.
Everybody? You want me to explain again how it came? Please say something. Okay, cool. Look at this. Now, okay. This structure you understood? The normal structure?
Yes, sir.
Okay, normal structure is okay. Now coming back here, see, this 2 oxygen atoms are same, right? Same way, this oxygen atom and this oxygen atom, nothing is changed. The only thing I changed is this. So here you see there is a double bond here, correct?
Okay.
But
Right,
so what happened here? So here, instead of having a double bond, I'm giving this lone pair on sulfur as a coordinate bond to oxygen. thereby the octet of oxygen is satisfied. So I represent the bond like this. From
and-
sulfur to oxygen or a mark. So
Yes.
both the structures are correct. Okay. So I guess hope you got a very good picture of what is a coordinate bond, isn't it? Right. Okay. So we'll move on. Right. So we are talking about sigma bonds. Sorry. We're talking about covalent bonds. So in covalent bonds, I told you there can be three types of bonds. One is sigma, another is pi, and the next one is coordinate. Okay. So let me ask you a question. What is the difference between a sigma bond and a pi bond? What is the difference between a sigma bond and a pi bond?
The sigma bond is head-on overlap. Pi bond is
Okay.
lateral overlap.
Exactly. So it's all about how the overlap of orbitals are happening, right? It's all about how the overlap of orbitals are happening, right? So in case of your sigma bond, I'm going to have head-on collision, head-on overlap. And in case of your pi bond, I'm going to have lateral overlap, right? Fine. So tell me, so in a sigma bond itself, I can have different orbitals overlapping. I can have S overlap, SP overlap, PP overlap. Can I have a PD overlap in sigma bond?
No, sir.
Exactly. So D will only form pi bonds. That's what you need to understand, right? And same way, if you look at the strength of these overlapping, the extent of these overlapping, since S orbital is spherically symmetrical, right? You will see that wherever S orbital is there the overlapping is more efficient. So say obviously SS overlap is stronger than SP overlap, SP overlap is stronger than PP overlap, correct? And so obviously since I have head-on overlap, sigma bonds are always stronger than pi bonds because lateral overlap not that efficient overlapping, right? Same way, if I go to my sigma pi bond, right? Again in pi bond I can have two types. What are they? P pi, D pi, D pi. Oh, sorry, three are there. P pi, D pi, and D pi, D pi. PD, PP, and DD. All these are the types of overlapping I can have, right? So again, in that I can look for the what to say? I can look for the strength of overlapping. Say P is little symmetrical, right? So wherever you have P in pi bonds, there it is going to be stronger. So obviously PP overlap, that is P pi overlap, is going to be stronger than what is that? P pi D pi, and lastly D pi is the weakest of them all. Okay, fine. Let me look at this. Okay, let me ask you. Say I have okay, O double bond O. Okay, I have O double bond O, and I have S double bond S. Okay, this actually doesn't exist. It actually exists as S8 molecule. Only oxygen exists as O2 molecule. Sulfur exists as S8. Anyways, theoretically, right? Now tell me which bond is stronger. O double bond O is a stronger bond, or S double bond S is a stronger bond. And I'll obviously want the one with the reason. Think and tell me. Use your brains. Just now, I just gave you the idea of how to look at it.
Like I have a question again, sort of breaking for me.
I'm telling I have O double bond O and S double bond S. Which bond is stronger? Or in other words, if I want to make it more technical, which will have higher bond energy? Bond energy means the energy required to break the bond. Right? So anyways, obviously stronger the bond is, more and more energy has to be supplied. Look at what are the orbitals overlapping here in both the cases. Please look into it.
Sir, I think O bond is stronger.
Okay, correct. Why?
Because there's only p orbital, it goes to maximum p orbital, whereas for s it goes to even d orbital. So p
D
pi p
orbital.
pi.
No, it doesn't go to d orbital. Okay, this is a question actually which will kindle your mind. Now please look at here. First, when I look the OO single bond, now you can remember that I have basically 1s2, 2s2, 2p4 for your what is that? Oxygen. Again, same for that oxygen. Same here also I have 2p4. So in 2p4, okay, there are 2 electrons, right? Say first, always the first bond is always going to be a sigma bond. Done. First bond is always going to be a sigma bond. So I will tell that this p orbital and this p orbital, right, will come to overlap head-on collision to form this sigma bond. Okay, and obviously again, now the pi bond has to be formed, and the second bond is always going to be a pi bond. So now what is going to happen? This bond and this bond will, this electron and this electron, 2p electron, 2p electron will come together to form the pi bond. Okay, now looking at here, S single bond S, if I take S single bond S, if I take, right, now in S, I know it like it's the next element after oxygen. So if it is 2p4, this should be 3p4. Hope you remember periodic table, right? Now this is 3p4. So in 3p4, I know how it's same thing only, right? Same way for this also it is, right? Now if you look at what orbitals are involving here, here it is 2p and 2p forming a sigma bond, and same way 2p and 2p forming a pi bond, right? 2p and 2p forming sigma bond, 2p and 2p forming pi bond. But there, which orbitals? 3p orbitals are involving, right? So 3p forms first sigma, and the next 3p and the next 3p forms the pi. Is there any doubt till now, guys? Okay, fine. So here in O double bond O, here it is 2p orbitals which are involving. In S double bond S, it's basically going to be 3p orbitals. Now please understand this also. So in p pi itself, I can have difference. Say like this, I can have 2p orbitals involving, or I can have 3p orbitals involving, or in some cases I can even have 2p and 3p orbitals involving. Say if I give you an example, if I give SO2, sulfur dioxide, right? Now same thing, I have S having 3p4, oxygen having 2p4. So here you can understand that 2p and 3p orbitals are involving in SO2 bond, in SO2 molecule, correct? Now in all these cases, then how will you decide which will have more effective overlap or which is going to be a stronger bond? Now it is all going to be about the size of the molecule, size of the orbitals, right? So the smaller the orbital, more effective will be the overlap, right? Smaller the orbital, more effective will be the overlap. So in this case itself, I can go for some sub classifications. So in p pi itself, right? P pi itself, 2p overlap is definitely stronger than 2p 3p. Same way, it is stronger than 3p and 3p. It is very rare to see molecules after this. That is 4p, very rare, very rare. Okay, so in general, 2p overlap is more stronger or more efficient than 2p 3p, and 3p is less stronger or weaker than 2p 3p. No doubt. So now which is the answer now? O double bond O or S double bond S? Which is stronger?
O double bond O.
O double bond O, because there are 2p orbitals involving. Okay, fine. Now if I ask you this question now, I have HF bond and I have HCl bond. Okay, now which do you think, which bond is stronger? HF, HCl, which do you think is stronger? Same analogy. But here there is no case of pi bonds. There is only sigma bond is there. But same thing. Okay, answer my question. Which orbital of hydrogen is involving in the bonding here?
S orbital.
Which s orbital?
1s.
Okay, 1s. So here also it's same. 1s only. Okay, fine. For fluorine, which orbital is involving in the orbital overlap? Atomic number is 9. So can I say the
2p5.
configuration? So 1s2, 2s2, 2p5. 1, 2, 3, 4, 5. Same way. For chlorine, it would have been
3p.
valence shell configuration. 3p5. Fluorine, chlorine, next element in the same group. Right? So chlorine would have had 3p5. So now look at this. Here I have 1s and 2p sigma bond. Right? Here I have 1s and 3p sigma bond. Now what is the answer for this question? Which bond is stronger?
HF bond.
HF bond, obviously, because 2p is smaller, right? So smaller orbitals will have more effective overlap. 3p is bigger, just like the case here. Okay. See, I am not hearing any answers. Bhavadarini, Divya, everybody understood. Shruti, Surya, Venisha, Abhishek.
Yes, sir.
See guys, you have to open your mouth and tell S, because this is little complicated things which you're seeing here. If you don't tell me yes, I will keep on repeating this. That's what is going to happen. And you are going to get bored. If at all you don't want that to happen, please make it interactive. Whenever I ask you, did you understand? I want everybody to unmute yourself and say yes. I don't want only one person or two persons answering yes. Is it understood?
Yes,
Yes,
sir.
sir.
Very good, very good, very good. This is how
Yes,
it should
sir.
be. Okay, cool. So now, we understood that here it is 1s, here it is 2p. Right, s and 2p orbitals, so higher overlap, say effective overlap. Here it is 1s and 3p, not that effective overlap. So definitely HF bond is a stronger bond than HCl bond. Okay, guys, first we saw Lewis theory, right? We saw the Lewis dot structures. What was the next theory under which we are seeing all this? Tell me. This orbitals overlap, all this. Under which theory are we seeing all this?
I didn't understand, sir, the question.
So basically, we saw Lewis dot structures. Lewis theory was the first. Lewis was the first one to understand or say talk about the covalent bonds and stuff, right? So we said that there are problems in Lewis theory because it is purely based on octet rule, right? So I can have more than 8 electrons in the valence shell. I can have less than 8 electrons in the valence shell. So we went on to next theory, and under that theory only we are seeing all the things. Basically, whatever we are seeing now. What was that theory?
Bond theory.
Just bond theory, or is there something else before the bond?
Valence bond theory.
Correct. So it is valence bond theory, VBT, right? So can you remember what was the statement told by VBT? What is the statement for VBT?
A covalent bond is formed when the unpaired electrons in the valence shell of an atom gets paired by overlapping of an atom.
Very good. Very good. Very good. That's exactly what we are seeing here. There are going to be unpaired electrons everywhere, wherever you saw, right? There are going to be unpaired electrons. And these unpaired electrons, as orbitals, are going to come together. That is, they're going to overlap to form a coordinate bond so that the unpaired electrons gets paired. That was the statement, isn't it? The unpaired electrons in the valence shell of an atom will come together. That is, they overlap to form a covalent bond and they get paired. So all the things, whatever the overlap, pi, sigma, head-on collision, all these things comes under valence bond theory. Okay, right. Now, but there are still problems here, right? Even though it is not based on octet rule. So you can see that I can have say more than 8 electrons also, less than 8 electrons also. All these things are fine, but there is a problem, right? What problem? I will tell you. Okay, so let me take the molecule of methane, which you are very much familiar with, isn't it? CH4. Okay, now let me see what is happening in carbon and hydrogen. Okay, fine. So for carbon, I know I have 1s2, 2s2, 2p2. Correct? Hydrogen, no problem. Hydrogen is having 1s1. That is not a problem at all. Carbon is a problem actually. Okay, so in 2s, I have 2 electrons, and in 2p, I have 2 electrons. No problem. Okay, fine. Now, according to valence bond theory, tell me, forget about this particular molecule. Forget about CH4. Talking about carbon. Carbon can have how many bonds? Now, I'm not talking about in real life scenario. According to VBT, how many bonds can carbon form? Looking at this and tell me.
2, sir.
Exactly, correct. It's 2 because valence bond theory says only the unpaired electrons in the valence orbital, valence shell, will involve in bonding, right? Again, I repeat, only unpaired electrons in the valence shell will involve in bonding, right? Now, this is the valence shell, right? In that there are only 2 unpaired electrons, correct? Right? That means what? It can form only 2 bonds. Right? But look at this molecule, CH4, that means there are 4 CH bonds. That means carbon is forming 4 bonds, not 2 bonds. Right? So VBD doesn't explain this. Right? Not only like this, there are so many other molecules, right, which have, or I can even tell if I take the example of PCl6, there's a compound, phosphorus hexachloride. Right? So if I look for phosphorus, I know it belongs to nitrogen family, so this will have 3p5. Isn't it? So if I look at 3p5 only, no? Sorry, 3p3. Right? Nitrogen will have 2p3, half-filled configuration. Same way, phosphorus also will have half-filled 3p3. Okay. So if I look at 3p3, now there are obviously I have 3s2 also. This is 3s, this is 3p. No problem. Now tell me, how many bonds can 3p? How many bonds can phosphorus form according to VBT?
3 bonds.
3 bonds because there are only 3 unpaired electrons. But look at the number of bonds formed here. Oh, it's not PCl6, guys. It is PCl5. Sorry. Right. Anyways, doesn't matter. So I have, according to VBT, I can form only 3 bonds. But look at the number of bonds formed between phosphorus and chlorine. It is 5 bonds. Again, it's not explained. Okay, so what are we going to do about it? Right, for this we have to see the next theory. Which is the most important of them all, right? Because a marks point of view, that is your examinations point of view, or say in understanding point of view, understanding chemistry point of view, both the things are very, very important for the next theory which I'm going to see. Okay, fine. Is everyone ready? Guys, you can ask whatever doubts you have right now, right? Because that particular thing is going to be an entirely new concept. But anyways, it's going to be interesting. We're going to make it easy. So guys, any doubts till now? Any doubts?
No, sir.
No, sir.
Awesome.
Okay. Thank you so much. Fine. So now we will go to the next theory. Okay. So there are actually going to be 2 theories. I'm going to club them both, right? There are going to be 2 theories, and both the theories I'm going to club together, and we're going to study it together. Okay, so there are 2 theories. First one is what is called as theory of hybridization plus. One more theory I told you we're going to club, that is my VSEPR theory. Okay, theory of hybridization and VSEPR theory. Okay, the full form is valence shell electron repulsion theory. Anyways, we'll see it. What is that? Don't worry. Okay, so all the problems we saw in case of a BBT, right? All those things are going to get overcome. We're going to overcome all these problems, almost all the problems. Okay, and even after this, we'll still have some more problems. But for that, we have one more theory after this, and that is the last, and that's why we're using it now in real life. It's not like we're not using all this, but that is the most accepted one. The next one which you're going to see. Okay. Anyways, so first we'll see what is theory of hybridization. Okay. Now this theory of hybridization is going to actually come, like it's going to overcome the problem what we saw in VBT. Exactly. So basically, say in case of your carbon, it says that according to VBT, only 2 bonds can be formed, right? But in reality, I know that I'm going to form 4 bonds, right? So those kind of problems are overcome in case of a theory of hybridization. Okay. So what it says, theory of hybridization, what it says is, now till now in VBT, what you saw is the atomic orbitals are actually overlapping to form a covalent bond, isn't it? Right? On your VBT, we saw that atomic orbitals are coming together, overlapping to form a covalent bond, right? Now, what theory of hybridization says is it is no more going to be atomic orbitals, right? It is not, I am not going to speak about atomic orbitals anymore. There are going to be some kind of special orbitals. There are going to be some special orbitals, and these special orbitals are what are called as hybrid orbitals, right? These new orbitals, it's not atomic orbitals, it's not like SPDF what you see in VBT, right? I'm going to form a new thing called as hybrid orbitals. Okay, fine. Now sir, the first question is, so what are these? What do you mean by hybrid orbitals? How are they formed? All these questions will come to your mind, isn't it? So please understand, right? So a hybrid orbital is basically formed by mixing of pure atomic orbitals. That is, say I have some atomic orbitals, S, P, D, F, all these things are there. Now I'm going to mix them together. That's not overlapping. Please don't confuse with overlapping, right? These are actually mixing, right? Overlapping is just coming together to form a covalent bond. That is different. Here, the hybrid orbitals are formed by mixing or adding your 2 or more atomic orbitals. 2 or more atomic orbitals. Okay, fine. So now there are certain rules which you have to follow for making the hybrid orbitals. Okay, the first rule regarding hybrid orbitals is that the number of atomic orbitals combining. Guys, one more thing. If you are not going to take notes for this particular thing, it is going to be really tough for you. I'm telling you now itself, because your book will not explain how much I'm explaining, right? So please do take down your notes. Okay. So the first point regarding hybrid orbitals is that the number of atomic orbitals combining. So obviously I told you so many atomic orbitals has to combine together to form the hybrid orbitals. So the number of atomic orbitals combining should be equal to the number of hybrid orbitals formed, right? The number of atomic orbitals combining should be equal to the number of hybrid orbitals formed. Okay, right, cool. This is the first thing which you have to understand. The second thing is that all these things we are doing, the hybrid orbitals, all these things we are doing, these are only for central atom. These are only for central atom. So I hope you remember, hope you know what is central atom. For example, if I take H2O, oxygen is a central atom. If I take H2SO4, sulfur is a central atom, right? So we are doing all this only for the central atom. All these hybridized orbitals exist only for the central atom. For the side atoms, it is only pure atomic orbitals. Okay. So remember,
I have a doubt.
yes.
So the atomic orbitals we are combining will be the central one.
Exactly.
The central
exactly.
one alone.
Exactly. Yeah. Yeah. Only the central one. The atomic orbitals which are there for the central atom only will take and combine them. That's it. We are going to do nothing with the orbitals of bond side atoms. Okay.
Okay,
So
sir.
only for central atom I have the hybridization. For the side atoms, it is still the pure atomic orbitals. Right? For the side atoms, it is still only pure atomic orbitals. Okay. Fine. So here also I'm going to see some overlap, right? Just like how we saw in your VBT, I saw pure atomic orbital of the central atom, pure atomic orbital of side atom were combining, right? Here, the only difference is the hybrid orbital of central atom and the pure atomic orbital of side atom will overlap to form a sigma bond. Is it understood? What I'm telling is, so what I'm telling is in VBT, we saw that central atom is there, side atom is there, right? Both of these pure atomic orbitals will overlap to form a sigma bond or a pi bond. Correct? Here, the only difference is, here also I'm going to have overlap, but the only difference is for the central atom, it is the hybrid orbitals which will overlap with the pure atomic orbitals of the side atom. That is the only difference. Okay, fine. So these 2 points are very important. Number of atomic orbitals combining should be equal to the number of hybrid orbitals formed. And for the central atom only, we speak about the hybridization. For the side atom, it is still the pure atomic orbitals. And here, the overlap is happening between the hybrid orbitals of the central atom and the atomic orbitals of the side atom. That's it. Okay, fine. Now, you don't have to worry about what are the different types of hybridization I can have. There are only few. I would say there are only 6 or 7 hybridizations are possible. Okay, so let me go into that. So we are going for, we'll speak about VSE PR in a little while. Wait for it. Okay, so we are still in the rules. Okay, so now what are the types of hybridization? Right. Okay. Now you have to keep this in mind. Number of atomic orbitals is equal to the number of hybrid orbitals. Okay. So first case is that one s orbital and one p orbital will combine. Right. So there is one s orbital, one p orbital. Totally 2 atomic orbitals are combining. Okay. So this will form a hybrid orbital just like this. Sp. This is the hybrid orbital. You should not call it as separately. This is one particular entity. So this is my hybrid orbital, sp hybridized orbitals. Okay. Now the question is, sir, how many such hybrid orbitals will be formed? The answer is here. 2 atomic orbitals are combining. So definitely there should be 2 numbers of sp hybridized orbitals. Okay. So this is the first type of hybridization. Okay. Now second one is s and 2 now it's not 2p orbital, it is 2 numbers of p orbital. Don't confuse here, right? There are 2 numbers of p orbital, not the 2p. 2p orbital is different, right? Here it is 2 numbers of p orbital. Now how many total? 3 atomic orbitals are combining, 1 s and 2 p's. So I will form 3 numbers, obviously 3 numbers of sp2 hybridized orbital. Very simple. So 1s and 1p, sp. 1s and 2p, sp2. Okay, and 3 numbers of them because there are 3 atomic orbitals combined. Cool? Right. Now next type of hybridization I can have is s plus 3p. Again, not 3p means not 3p orbital, 3 numbers of p orbital. Okay. So now totally 4 orbitals are combining. So definitely there are going to be 4 hybrid orbitals of sp3 hybridized orbitals. Okay, next. Can I have s plus 4p? Guys, can I have s and 4 numbers of p orbital? Can I have that? Did you understand my question?
Yes, sir.
I'm asking, can I have s and 4p, 4 numbers of p orbitals? Okay, I'll tell you the answer. The answer is we cannot. Can you tell me why?
We can only fill till 3.
Exactly. So the maximum number of states for P is only 1, 2, 3. I don't have a fourth P. Are you able to understand? Right. So basically, there are only 1, 2, 3. 3 P orbitals are possible. Right. I don't have one more, so I cannot have 4 P. So this is the only thing. With S and P, only these 3 are possible: SP, SP2, and SP3. There is no 4. Right. So this is something to understand, something to remember. Okay. Next. So after P is over, now I can go for d orbital. That is the next case, right? So S plus 3p plus 1 d orbital, right? S plus 3p plus 1 d orbital will form now how many? 1, 3, 1 plus 3, 4, 4 plus 1, 5. There should be 5 numbers of sp3 and one more is d. sp3 d orbitals, hybrid orbitals. Okay, next S plus 3p plus 2d orbitals. Right, now I can have 6 numbers of sp3 d2 orbitals, hybrid orbitals. Now last one is S plus 3p plus 3d will form 7 numbers of sp3 d3 hybrid orbitals, but this is very rare. The last one we saw is very, very rare, but all the first 6 are very much possible. Okay, so remember sp, sp2, sp3 done. After that, I have to go for d orbital, sp3d, sp3d2, sp3d. Very simple. Okay, right? So these, again I repeat, these are only for central atoms. These are only for central atom. These hybrid orbitals will overlap with the atomic orbitals of the side atoms, and they form a sigma bond or a pi bond. We'll see. So I'll generally say that a bond is formed, a covalent bond is formed by the overlap of hybrid orbitals of central atom and the atomic orbitals of the side atoms. Right? So guys, any doubts till now?
No,
Is
sir.
everything clear?
Yes, sir. Clear,
Okay.
sir.
Cool.
Yes, sir.
So these are the different types. The names you have to remember, the names of the orbitals, along with the numbers. How many such is forming? It's very simple only. You know, you can see 1 plus 3, 4, 4 plus 1, 5, 5 here. So it's very easy to remember how many and what are the hybrid orbitals. Okay, fine. So this is one thing which you have to know. Okay. So if at all you, this is that, please understand that this theory of hybridization is basically only a purely mathematical concept. Okay, this is purely going to be a mathematical concept. So in reality, if you want to see that all these orbitals are there, in reality they are not actually existing, right? So this particular form of explaining, that is with the help of these hybrid orbitals, we are able to overcome the problems we face in VBT. Okay, but in practical cases, this really doesn't exist as such, right? Whatever the hybrid orbitals you saw, right, are actually not going to exist in reality. It's purely a mathematical concept, but it's a very useful concept. That's what is very important. Well, then why are we studying it? It's because it is going to be really useful, right? It is going to help me find out the shape of the molecule, the structure of a molecule, the bond angles, the bond strengths. All these things can be understood if I know hybridization. Okay, fine. So we understood what are the types of hybrid orbitals, and I told you that hybrid orbitals are going to exist only for central atoms, right? But sometimes there can be problems, right? There can be problems in choosing. There can be problems in choosing what will be the central atom, right? In choosing what will be the central atom. Say for example, if I have HCN, right? So how do you choose which is the central atom, right? Because I have 3 different atoms here, right? So how will I choose which is the central atom? Now this is the rule which you have to follow. Central atom is the one which should have least ionization enthalpy or ionization energy, and that should be the one which should be central atom, right? So in this case, carbon will be the central atom. In this case, carbon will be the central atom, but you will not face all these problems. right? I'm just telling you, in a complicated case, if you're not able to find, right, just know that central atom is the one which will have least ionization enthalpy. Okay, I can give you a logical reason for why this is like this. Like say, why I should have least ionization and energy. It's because you know that the central atom is the one which is going to share all its electrons, right? So obviously the electron has to little come out of the nucleus and get shared. So obviously the energy required there should be minimum so that it is able to easily undergo the bonding. Okay, so anyways, this is not that important. Fine. Now I am going to give you a trick, right? I am going to give you a trick to find out what will be the hybridization of the central atom in whatever molecule you have. Whatever molecule you have, I will be able to find what is this, I mean, what is the hybridization of the central atom. We'll be easily able to find out. Okay, but before that, continuing with the points, now please understand that pi bonds will not be present, will not be there in the hybrid orbitals. So just take down this point now. When I actually go for the hybridization, when I go in depth, you will understand why is it like this, right? Pi orbitals, basically you see that in valence bond theory, both the pi bond and the sigma bond is formed by the overlap of the atomic orbitals, right? So here in theory of hybridization, sigma bond is formed by hybridization of hybrid and the pure atomic orbitals, but your pi bond is still only pure atomic orbitals overlap. Pure atomic and pure atomic, right? Please know this, okay? In your sigma bond, we're talking about hybridization here. In theory of hybridization, the sigma bond, yes, the central atoms is hybrid orbital and the side atoms is pure orbital. Yes, but in case of your pi bond, if I have a pi bond, now that should be between the pure atomic orbital of the central atom and the pure atomic orbital of the side atom also. Okay, and one more thing, if I have lone pairs on the central atom, if I have lone pairs on the central atom, they will be placed in the hybrid orbitals, right? If I have lone pairs present on the central atom, again, bonding atom doesn't have any hybridization, so we don't have to even talk about it, right? But if I have lone pairs on the central atom, right, that should be placed. Obviously, you have so many numbers of hybrid orbitals. Say I can have 4 numbers of sp3, 3 numbers of sp2, so on and so forth. In one of them, there should be a lone pair. If at all there is a lone pair, it should be there in that hybrid or in one of those hybrid orbitals only. Okay, so now just going about the points. First point was the number. Now the thing is, in theory of hybridization, it is not anymore going to be overlap of pure atomic and pure atomic. It is going to be there's going to be something called as hybrid orbitals, which are going to be formed for the central atom, right? And especially a sigma bond, right, is going to be formed by the overlap of hybrid orbitals of central atom and the pure atomic orbitals of the bonding atom. But pi bond is still pure and pure atomic orbital central atom, pure orbital of the side atom also. And next thing is that the number of atomic orbitals combining should be equal to the number of hybrid orbitals formed. You saw sp will have 2 numbers, sp2 will have 3 numbers, sp3 will have 4 numbers, right? That is next. And lastly, okay, before that, you are going to do hybridization only for the central atom. You do not care about the bonding atoms, that is the side atoms. Okay, and lastly, you have to remember that the lone pairs must be placed in any one of the hybrid orbitals of the central atom. Again, lone pairs on the central atom only, not the lone pairs on bonding side atoms. Okay, lone pairs on central atom should be placed in the hybrid orbitals, in any one of the hybrid orbitals of the central atom. Okay, so these are all the rules, right? What is the time? Okay, we don't have time, guys. So now we will continue with this. So next class, I will be giving you a shortcut to find out the hybridization of any molecule given. Any molecule in 1 minute, you'll be able to find the hybridization. But you are not going to use this trick in your school. Okay, means because if you use the trick and write the answer, they will not give you marks, right? But you can use this trick, find the hybridization, and show how the hybridization is happening. That is the smartness, right? Know the hybridization, then go for the diagrams which I'm going to tell. Anyways, we'll see all this next class. So guys, until then, thank you. Bye bye.
Yes, sir. Thank you, sir.
Thank you.